The known universe is full of treasure, if you know where to dig.
Holy cow! It's fun just like blowing stuff up.
We're on a quest for cosmic riches. Each treasure more precious and harder to find than the last. From gold and diamonds to endless power and even the key to life itself. How far will we push?
Supposedly, I'll be able to walk on water.
More than likely, you're going to sink.
But there's something good down there.
How much will we endure?
This is not a trick. This is what I actually sound like now.
Strap in, because we're going to the ends of the universe on this cosmic treasure hunt. An asteroid about the length of the island of Manhattan is on a collision course with North America. It will strike the Earth with the destructive power of 10 billion Hiroshima bombs. But this menacing beast won't destroy our planet. It will be responsible for creating over $1 trillion worth of treasure.
Treasure is something that's very useful or desired, and something that's extremely hard to find.
Here on Earth, everybody knows what treasure is. It's gold, silver, diamonds.
Treasure comes in all different shapes, sizes, and most important of all, values. And we're about to search for the biggest prizes the universe has to offer. The first stop on our galactic treasure hunt is right here on planet Earth. A small town in Ontario, Canada, where one type of treasure, precious metals, is big business.
Here we are in the Sudbury Basin of Canada, home to one of the largest metal deposits in North America. Over $1 trillion have been mined from this area over the last century. We have copper and nickel as some of the main products, but in addition to that, we have platinum as well as gold.
Sudbury's big haul is nickel, mining up to $2 billion worth in a year. But the fact that there's gold and other extremely valuable metals mixed in with all this nickel makes Sudbury a very mysterious and profitable place.
So here we are in the northern part of the Sudbury structure, over 500 feet underground. The ore deposits form veins, long linear systems. They're only about 1 foot wide. It almost looks as if someone's taken a paintbrush and just painted them on. And so even though this is only 1 foot wide or so, it actually extends for hundreds of feet above us and hundreds of feet below us. So this vein system in here is worth millions of dollars. Many ore deposits in other situations in the world typically are dominated by one main metal. The intriguing thing about Sudbury is that it's got with many different metals, and it's probably only one of 2 places in the world which has such a rich variety. This is made up of copper, used, for example, for wiring in your home, but also palladium and platinum. And we would use platinum, for example, for the catalytic converter in your automobile. In addition to that, gold, which is of great economic value.
Gold is just a small part of the rich veins running through Sudbury, yet it still totals hundreds of millions of dollars in today's prices. And this treasure's uses go beyond coins and jewelry.
People like to have gold stuff. It's able to conduct electricity, it can reflect light, it's malleable. You might consider that to be the ideal treasure.
But as many people throughout history have found, gold is elusive. If we put the amount of gold produced in the entire world each year in one cube, it would fit in the average person's living room. And if we took the amount of gold produced throughout all of human history, it would only build about 1/3 of the Washington Monument. So why is there so little gold in the world?
Gold is difficult to find on Earth because it doesn't form other compounds like other metals do. So these other metals float to the surface of the Earth, but because the Earth has this strong gravitational pull, it pulled most of the gold towards the core of the Earth.
But in Sudbury, early miners found gold mixed in with all of the other metals. It's a sign that something here is different.
So how do we know how the Sudbury Basin was actually formed? These are called shatter cones. We cannot make these from dynamite or even a nuclear weapon. The only way you can form these special conical fracture systems is by the hypervelocity impact of an asteroid hitting a planet.
The evidence of an asteroid impact soon reveals a shocking twist. Scientists discover that this was no ordinary asteroid.
The asteroid that hit in the Sudbury region in Canada was the second biggest asteroid that we know of to ever hit the Earth. Certainly it was an extinction class event.
This is the same massive asteroid that hit North America 1.85 billion years ago. And it's the creator of Sudbury's huge treasure chest. But how does it pull off this impressive feat? When it hits, the asteroid creates a bowl-shaped crater around 100 miles wide. At the bottom, molten rock and liquid metal begin to churn at temperatures more than twice as hot as lava from a volcano. Inside this swirling inferno, copper, nickel, and other valuable elements, including gold, are sinking to the bottom, and then start to form rich veins deep inside the crust. On the surface, the liquid rock cools, forming a hard sheet that covers over the valuable deposits, creating a cache of buried treasure waiting to be discovered. And that's just what engineer and astronaut Mike Massimino and scientist Steve Jacobs hope to do with an air cannon, metal ball, and block of ice.
An asteroid impact seems pretty simple. Boom! Big hole in the ground. Well, all that Sudbury treasure didn't end up where it is by sheer luck. There's a reason it ended up there, and this little cannonball is going to show us why. What we're hoping to create is a small version of what happened at Sudbury. This cannonball is going to be the asteroid. A block of ice is going to represent the area at Sudbury. And we're going to fire this thing into that block of ice. What are we going to do with this thing?
We know there will be a crater or a hole or a depression.
Makes sense.
That makes perfect sense.
Yeah.
But that's not exactly what we're interested in. There's going to be possibly some other phenomena. Because when that asteroid comes towards the Earth, it's got a lot of kinetic energy.
Yeah.
And then all of a sudden it hits the Earth. And where does the energy go?
It's got to go into the Earth.
It's got to go in the Earth.
When energy like that hits the planet, a crater is easy to locate. But there's a lot more going on around it than you'd realize, unless you take a closer look.
Are you ready to launch this asteroid?
I'm ready to launch it. How about you?
I think we're going to see something really neat.
3, 2, 1.
was great.
Oh my goodness. You know, it's cool. I mean, it's fun just like blowing stuff up.
Well, check this out. This is incredible. You can tell where it impacted. Right here,
Yeah.
everything's kind of mashed, right?
Yeah.
And a lot of transfer of energy. That's what blew all the ice off,
Yeah.
right? So that's kind of a inverted crater. But what was left behind? Don't ignore this for a second. Look around and see what you see all the way around the impact site.
Yeah, you see cracks, and you
Yeah.
see what's interesting is you see the cracks inside.
This web of cracks is where the treasure is hiding.
Here's some liquefied minerals represented by this dye. If you see a fissure or a line, just kind of dribble that on there. Let's just see what happens. And kind of go over the whole surface of that.
Yeah,
you can see it going down the cracks inside. That's just amazing. Look at the pattern that's being created.
So what was cool about the red liquid is it actually illuminated the cracks and fissures. We created them, couldn't see them so well just by looking at them, but then the red liquid made them come to life.
And just like the dye, after the asteroid impact, gold and other metals find these cracks and fill them in, forming a hidden vault of precious metal veins.
The little veins that were created inside the block of ice, just like they were created in Sudbury.
After scientists figured out how these stores of underground treasure were created, another question still remained. Where did the precious metals originally come from? Many theorized that they arrived on the asteroid itself, an intergalactic treasure ship that crashed to Earth.
Asteroids and comets, they giveth and they also taketh away. We talk a lot about how asteroids and comets create mass extinction, for instance, the dinosaurs. What we don't talk about as much is how they actually bring heavy metals to Earth.
But looking closer at the makeup of the ground and rocks around Sudbury shows that this treasure wasn't a passenger on a traveling rock. Its origins were much bigger.
So one of the big mysteries about Sudbury is actually where the metals came from. And if we look at these rocks here, we'll get a clue.
Normally, minute atoms of metal would be spread throughout the rocks in this area. But that's not the case here at Sudbury.
If we look in detail at these for metals, we wouldn't find any. The metals have sunk to the bottom.
What this means is that before the asteroid, the gold and other metal atoms were all too small and widely dispersed to mine. But when the asteroid hit, the impact caused the gold atoms to melt and fuse together into rich mineable veins.
In many ways, I think it's true to say that the treasure was already here in the Sudbury region before the impact, but the impact itself concentrated those treasures into truly phenomenal economic deposits.
How gold and other metal deposits form is one of Earth's most complicated processes. But it's nothing compared to what it takes to form another valuable treasure. One that grabs even more attention than gold. Diamonds.
Diamonds are cool because they're sparkly. So that's why most people like them, but I like them as a scientist because they're like crystalline carbon. That's pretty cool. And they're super hard and they're super rare. So all those things combined make them very valuable.
A diamond forms when you have carbon graphite and it's exposed to both intense pressure and very high temperatures. You need both in order to basically crush and then form this diamond.
The largest diamond ever found was the Cullinan diamond, weighing in at 3,106.75 carats. Its price tag was estimated at over $400 million. Not a bad payday for a lump of carbon. A diamond is an extremely valuable commodity and pretty hard to find. Why? It has to do with the severe conditions needed to create them, nearly 100 miles below the surface. Here, deep inside the mantle, temperatures liquefy metal and pressures approach 1 million pounds per square inch. It's hell on Earth, but the perfect environment for carbon atoms to crystallize into diamonds. In order to reach the surface, the diamonds hitch a ride from a burst of blazing magma, traveling at supersonic speeds. The sudden rush creates a kimberlite pipe, a cone-shaped structure that reaches the surface and encases the diamonds in the rapidly cooling rock below. So how does carbon deep inside the Earth transform into diamonds?
Diamonds are the hardest substance known to humankind. The carbon atoms are arranged in this crystal lattice such that the structure is so tight that you can't deform it, as it's produced under incredible pressure.
Pressure can accomplish some pretty unbelievable things. To see just how astonishing, astronomer Andy Howe is going to use pressure to turn a liquid to a solid and make the ultimate leap of faith.
We're gonna see if a couple of tons of cornstarch plus a little bit of pressure can allow me to walk on water. Oh, there we go. This is harder than it looks.
Yeah, it is. That's why you're doing it.
I'm wearing a wetsuit today because sometimes you just got to get out of the laboratory and get your hands dirty. So we've got a couple of tons of this watery goo. It's over in this dumpster back here, and supposedly pressure my feet is going to make this cornstarch into a solid, and I'll be able to walk on water.
What do I have here, Andy?
Looks like about a 10-pound weight or so.
That's exactly what it is, and I'm going to set it here. Let's see what happens to the 10 pounds. I'm going to set it right there, and whoops.
10 pounds, and it just goes right down.
It goes right down, yeah.
How's this thing going to support my weight? I weigh like 200 pounds.
Most of the liquids we deal with on a daily basis are Newtonian, which means that if I put a pressure on the fluid, it will exert that pressure over the entire surface of the inside of that container. So if I push a little bit right here, that amount of pressure will be spread out over the entire surface of the vessel that's containing it.
That's why if you try to walk on water, you'll be in over your head, because it continues to be fluid no matter how much force you put on it.
But this mixture of cornstarch and water acts non-Newtonianly, which means if I put a little bit of pressure here, the pressure doesn't spread quickly. It changes the molecular structure of the mixture temporarily into a solid, just for a few seconds.
This happens because cornstarch is made up of long chains of atoms, and when pressure is put on them, these chains get tangled up, becoming solid until they quickly untangle and go back to being a liquid. Just like coal turning to diamond, pressure changes the structure at the molecular level.
Quick action, change it, dance on this stuff.
Dance on this thing.
And it's a solid.
You want to test it first?
Oh, definitely.
Here, now take this little rubber ball.
All right. So it should bounce, right?
Should bounce, yes. Throw it right here.
That's not reassuring to me.
Let's try a little more mass.
All right, let's try
a little more mass. And throw it out there and see if that will bounce.
Oh, wow!
So that time we exerted enough pressure to solidify it instantly.
So that's what I'm supposed to do.
Just don't mimic the little ball, mimic the bigger ball.
I don't know about this stuff.
Look at this! Look at this! You did it! All right, man. Woo! Man, you made it. I'm glad. Do it again, do it again, do it again. Here it goes. Science came true, didn't it?
I gotta get a little aerobic shove.
Well, now think, all that 200 pounds of yours is applying a lot of pressure. It's changing the molecular structure And you'll see that in nature in a lot of places where molecular structure is changed via pressure.
So this is how, I guess, you turn carbon into diamond.
It's hard to believe, but each thump of a foot onto cornstarch has the same effect as 1 million pounds of earth pressing down on carbon in the mantle. And that pressure has to be continuously applied, or diamond will never form. And Andy will take a bath.
So if I stand still, I'm gonna sink.
More than likely, you're going to sink.
Hope there's something good down there.
And you're doing this for science, my friend. You ready to do this, Andy?
Yeah.
I'm proud of you, man. Go, Andy! Hey, Andy!
Man, this is the strangest bath I've ever taken. Why'd you put me in here, you crazy mad scientist?
You did the second half of the demonstration. The first, you showed what happens if you add pressure to a non-Newtonian fluid and you've stayed on top of it. But when you quit adding pressure, you sank. And you did that so elegantly.
But does it work both ways? Can pressure turn a solid into a liquid? John Eggert of Lawrence Livermore National Laboratory knows it can, since he's cranked up extreme pressures that have liquefied one of our greatest treasures.
So taking diamond and actually trying to get it to melt is difficult because if you do it in air, it'll burn. If you do it in a vacuum, it'll turn into graphite, and then the graphite melts. And so you have to actually go up above about 15,000 atmospheric pressures in order to melt the diamond phase.
In the laboratory, Eggert was able to create pressures 40 million times greater than a person feels at sea level. He then cranked up the temperature using a laser.
So we're taking 3 kilojoules of energy, which is equivalent to throwing a refrigerator off the roof of your house. That forms essentially a rocket-like force that sends a very large pressure wave into the diamond.
Using these extremes, he finally cracked the code and was able to measure what it takes to melt diamond.
The surprising thing that happened when the diamond melted was that the diamond would float on the liquid carbon.
Once Eggert realized that any remaining solid diamond floated on the newly liquefied diamond, he began thinking about where such extreme conditions might be found outside of the laboratory.
Where else in our solar system would we find the conditions similar to those where we found the diamond melted? The very high pressures, very high temperatures, and lots of carbon. The outer core of Neptune has very similar conditions and may very well represent the greatest trove of diamonds in our solar system.
A potential vast ocean filled with floating diamonds. But Neptune won't grant us easy access to its diamond stockpile. In order to reach it, we'd need to tear through the thick atmosphere of hydrogen and helium, with winds nearly 6 times stronger than the worst gusts ever recorded on Earth. Then we'd have to survive the lethal mantle made of water, ammonia, and methane that reaches temperatures hotter than the surface of the sun. But as we push past these blazing layers, the treasure-filled outer core emerges. The fluid metallic carbon would cover the surface and be littered with solid diamond icebergs. But mining this titanic score is just a pipe dream.
The ability to actually get to the core of Neptune to get these diamonds would be impossible. There's so much gravitational attraction that even if you could get in without being crushed, it would be impossible to be able to get out.
But there are other sources of vast riches in our solar system, and they may be much more obtainable. We've already seen how an asteroid hit formed the treasure chest at Sudbury. But asteroids themselves hold huge deposits of precious metals.
If we add up all the asteroids that we know of, the volume that it encompasses is only about 1/2000th that of the volume of Earth. Having said that, all the metals on asteroids combined add up to way more than what we've ever been able to mine here on Earth throughout their history.
Everything from copper to silver to gold can be found inside asteroids. The question is, how do we reach them? It's the beginning of a new kind of gold rush. A great extraterrestrial treasure hunt. Asteroids have been the source for well over $1 trillion worth of treasure. They can turn tiny atoms into a huge stockpile of riches, and they also tend to have treasure of their own. But no one's exactly hoping for one of these massive rocks to take a detour to our planet. If we want the treasure inside an asteroid, we have to go to them.
Where will we look for treasure in the universe? Well, asteroids are a pretty good place because you don't have to go as far as other planets.
The asteroid Eros will come within nearly 17 miles of Earth. Right in our backyard, astronomically speaking. The amount of treasure contained inside Eros is staggering. So staggering that this asteroid, approximately the size of Lake Tahoe, contains more metal than has ever been excavated in the history of human civilization. We could stack up the metal from everything we've ever built, from the Eiffel Tower to the Golden Gate Bridge. Every skyscraper, every car, all of it piled up adds up to only a tiny chunk of the metal contained inside Eros. With the resources contained inside this floating treasure trove, we could build an entire Earth's worth of structures on the Moon, Mars, and beyond.
The total value of Eros, if you count up all the metals that are in it, it's about $20 trillion. That's an incredible amount of value just in a single asteroid.
But the value of the treasure inside objects like Eros is a lot bigger than just a huge payday.
If we're going to colonize space, we need to become self-sufficient, and that means actually taking advantage of the resources that are out there as opposed to bringing it with us.
It costs money to take stuff with you. You know, they were coming to the New World hundreds of years ago. They were needed to build a house. It would be better if they came to the New World and they were able to use the trees that were already there.
But before we can even think about tapping into these loaded stockpiles, we need to reach one first. A few missions, like the 2003 Japanese probe Hayabusa, have briefly visited and even sampled some of our nearest rocky neighbors. But NASA has even bigger plans.
The human mission to an asteroid was outlined in the Obama administration's space policy goal to take place around 2025. So that's fairly quick. One of the goals, I think, for human exploration of an asteroid would be to get a fairly sizable sample to bring back to Earth so we can study the chemical makeup that might have seeded the early Earth with the building blocks of life. Well, one of the challenges for human exploration to an asteroid is that the asteroids don't have much in the way of gravity. So you just can't come down on the asteroid and start walking around. You would put yourself in orbit rather quickly.
An asteroid's lack of gravity is directly related to its small mass, making navigating one and eventually exploring it no easy task. Here on Earth, rock climbers seem to fight the same gravitational battle. But when we look closer, it's not exactly a perfect match. Something Professor Ian Garrick Bethel of UC Santa Cruz has been trying to nail down.
One of the greatest challenges in exploring an asteroid is the very low gravity. To affix yourself to the asteroid, you might use anchors, much like a mountain climber. However, on an asteroid, the surface is not covered in solid rock, but loose powder and gravel known as regolith. And if you put your anchor into this material, it would very easily come right out.
And without a way to attach to the asteroid, the lack of gravity rears its ugly head.
Something as simple as this would send you flying off into space. A mountain climber relies on gravity to keep him attached to a rock face. Without that gravity, mountain climbers would simply float away.
So is there a solution? Or will asteroids' treasure remain out of reach?
One way that you might be able to keep astronauts stable on the surface is to wrap a strong ribbon, like Kevlar, all the way around the asteroid if the asteroid is small enough. Then astronauts could use this to keep them affixed to the surface.
Ian's idea might just solve our problems of staying on an asteroid by keeping astronauts strapped to its surface. A Kevlar ribbon wraps around the entire rock and attaches to the explorer with a metal harness. A giant seatbelt that pushes the astronaut down, creating a type of artificial gravity that allows him to explore the entire surface and prevents him from flying off and losing his asteroid. Once we're able to master standing on an asteroid's surface, a seemingly limitless supply of metals will be at our disposal. But in terms of treasure, metal isn't space's most valuable prize. Our thirst for power will drive us to find the biggest cache of treasure yet. But unlike gold or diamonds, we can't touch it. We can't even see it. But it may become one of the most valuable treasures in the universe. Helium-3. Because it's missing one neutron, helium-3 is an excellent fuel to create energy.
Helium-3 is a rare isotope of helium that's basically used to create fusion without all the dangerous effects of radiation.
Fusion, or pushing atoms together to create energy, is the holy grail of clean, abundant power. And it's helium-3's potential as a fuel that has caught the eye of Dr. Jerry Kolsinski at the University of Wisconsin.
We've been studying the feasibility of producing the helium-3 reaction.
The problem is sustainable fusion power is still many years away. But that doesn't stop Kolsinski from taking the first steps.
The machine on my right here is called Helios. What we're seeing is fusion reactions. They emit light, and that's the glow that you see.
Seeing an 80% increase in the neutron rates with a 25% increase in the voltage.
If Kolsinski can perfect fusion on a large scale, then helium-3 could become the most valuable treasure in the universe.
1 ton of helium-3 would produce the electricity equivalent to 10,000 megawatt years of electricity, and that would serve a population of 10 million people for a full year.
The only catch is helium-3 is extremely rare on Earth, coming mostly from the decay of thermonuclear weapons.
If we want to do power production, electricity, we need tons of helium-3. The production from weapons is about 2 kilograms a year and dropping.
And that makes helium-3 very valuable.
I'm holding in my hand here about 1 liter of helium-3. Helium-3 now goes for a street value of about $3,000 a liter. To translate that, it's worth $8 million a pound.
But in space, helium-3 is much more plentiful.
The sun is the greatest source of helium-3, and the reason why we don't find it basically here on Earth is because we have a magnetosphere. This magnetosphere captures all of these particles. That means that helium-3 is much more abundant in space than it would ever be on Earth.
On the moon, there could be over 1 million tons of this valuable treasure.
There's enough helium-3 on the moon that if it was liquefied, could fill this entire stadium and would provide the present world energy use for 5,000 years.
But that's nothing compared to the vast quantities of helium-3 we could find in gas giants such as Uranus and Neptune.
If we looked at areas outside the moon, we'd fill all the stadiums in the Big Ten and provide energy for longer than anybody can imagine.
Finding huge stores of helium-3 may be the catalyst that ushers in the ultimate galactic gold rush. On Uranus, there's enough helium-3 to meet Earth's energy needs for the next 4 billion years. To collect this gas, scientists have proposed using giant balloons, a literal mine in the clouds, where the balloons heat hydrogen from the atmosphere so they can float in the sky and extract the valuable helium-3. At the base of the balloons is a factory that gathers in the gases and processes the hydrogen and helium into separate propellant tanks. A transfer ship docks with the balloon, collecting about 1,000 pounds of precious helium-3. And it also takes the hydrogen as fuel for its return trip. And the factory begins its process again. With just 1% of the helium-3 on this treasure-filled planet, we could power larger ships to travel to every star in the Milky Way galaxy and carry millions of passengers. Sounds too good to be true. Would it actually work? To find out, Mike Massimino has set up a test.
Mining gas can be a little tricky because you can't use your hammer and your chisel on gas.
Fortunately, there's a solution.
But what we can do is float something inside of that gas and collect it.
We can see how this works here on Earth by mixing 3 distinct gases in a tank, each with a different density: air, carbon dioxide, and something called sulfur hexafluoride.
So what is sulfur hexafluoride? I had the same question. But it is a gas that is 6 times more dense than air. And if I inhale it, my vocal cords will have to work a little bit harder to produce a sound. Kind of like the opposite of what happens if I were to inhale helium.
This is what it makes me sound like. This is not a trick. This is what I actually sound like now.
All right, here we go.
Mike is going to drop into the tank and release each gas separately, creating a mixture of gases, just like there would be on a planet we might want to mine.
We're just doing the sulfur hexafluoride right now.
This first extremely dense gas falls to the bottom of the tank, just like the lowest part of a planet's atmosphere.
All right, Mike, it's time to put in the second gas. We're going to put in some carbon dioxide, and it should, if all works well, float on top of the sulfur hexafluoride.
Helium-3 is like this layer of carbon dioxide. It floats on the denser atmosphere below it, but it's still separate from the less dense gas above it. Time to mine some gas. Or in this case, drop in a balloon that is heavier than air, but lighter than the sulfur hexafluoride.
Let's see what happens with the balloon. Eureka! That balloon overall is less dense than the layer of carbon dioxide, but lighter than the sulfur hexafluoride below it. Let me try blowing some bubbles. Let's see what they do. And look, we're floating on a layer of carbon dioxide. You see it? It's floating on the gas.
These bubbles, they're pretty light, so they're staying up high.
Yeah, they're staying up high, and at different altitudes because they have different mass.
So if we wanted to mine this lighter gas, we need a bubble. If we wanted another kind of gas that's a little more dense, you'd come down here with the balloon.
That's right. That's absolutely right. You have your own atmosphere.
And that's how we mine something we can't even see. We can navigate a maze of gases on a planet like Uranus using density to build a treasure map. But helium-3 isn't the ultimate catch. Beyond energy, there's one treasure we need more than anything else. The most valuable resource in the universe.
The most important thing we need to live is water. We need water. If we don't have water, we're in a lot of trouble.
The human body can be up to 65% water, and we won't last long without it. Fortunately, Earth has around 60 quintillion gallons for us to drink. But extreme temperatures in space and on other planets makes liquid water one of the rarest and possibly most precious treasures we could ever hope to find.
If you think a bottle of water is expensive on Earth, just imagine how much it costs in space.
With water potentially the most valuable treasure in the entire universe, scientists have tried to locate it in accessible parts of our solar system. And much to their surprise, in 2009, they found it a lot closer than they expected. With an operation called L-Cross.
There was this possibility of water on the moon. So L-Cross went there to help determine the potential of these things for further exploration.
That exploration keyed in on the one area of the moon that scientists believe had the potential to hold water.
When the moon goes around the sun, it never gets sunlight to the poles. And the floors of these craters, you will never see sunlight for maybe 1 billion, 2 billion or more years.
And it was in these craters where our most valuable treasure might be hiding. So L-Cross was designed to fire a probe on a suicide mission into the moon, while another piece of the ship remained in orbit to analyze the explosive debris.
This little inset, this little area here is where the impact cloud is. This is about 20 seconds after impact. We'll zoom in. This image here where we've enhanced the dust cloud so you can see it more clearly, this is about 6 miles across. We saw the ejecta come up, we saw water, and we saw water ice. The amount of water that we saw coming up into our field of view was about 150 kilograms or so.
That works out to about 40 gallons of water in just this one impact cloud. It seems like a small amount, but it revealed something that shocked many scientists.
When we look at how much dust we threw up and the water related to how much dust we threw up, we saw about 5% by weight water, about twice as wet as the average water concentration in the Sahara Desert. That actually is amazing to me, that there are places on the moon wetter than places on Earth.
Over the next year, scientists were able to determine that the crater L-Cross impacted actually contained about 1 billion gallons of water ice, enough to fill 1,500 Olympic-sized swimming pools. And with other sites in the polar region with the potential for more water, we may have finally discovered the treasure that unlocks the riches of the rest of the universe.
The treasure and the value of things change a lot in space. These things that are valuable here on Earth, they don't help you. Credit cards and cash don't go very far in space, but water and air and materials and things that are going to help you. It's more like a survival situation. What do you need to live as opposed to what do you need to decorate, you know?
We start out with mining stuff on Earth, like gold, that it takes to get us to space. We can go to asteroids where we can mine metals, and then we can go to the gas giants where we can get helium-3, and that will be fuel for even longer voyages. And then there's actually water out in the solar system. It's almost like the solar system is a treasure map.